Okay, so welcome everyone. So today it's my pleasure to welcome Matthieu Darcy, who will be talking about kernel methods and operator learning. Thank you, Matthieu.
Thank you, Bouendian, for the invitation. Thank you to all the organizers for leading and organizing this seminar. So today, what I'll be talking about is kernel methods and operator learning and how to use kernel methods for operator learning. My goal is also to give you an understanding of what operator learning is and the specific challenges that arise in data-driven operator learning, specifically for PDEs. So this work is joint work with Pao Bhatia from Caltech, who's with me. He's a PhD student with me at Caltech. Bamdad Hosseini, who is a professor at the University of Washington, and Huma Nawadi, who is professor at Caltech and my advisor. So the focus of this talk will be operator learning in the context of PDEs. So what is operator learning at a high level? So at a high level, the operator learning problem can be formulated as follows. You have n samples, ui and vi, from spaces u and v, and some form of operator that maps ui to vi. And generally, in this talk, we think of u and v as being spaces of functions. So u and v here are both functions, and g is some operator acting on these functions. The operator learning problem can be summarized as follows. Given this data, these n samples from these two spaces, we wish to approximate this true operator G dagger. So operator learning has been a very prolific field recently, mostly in the context of data-driven operator learning for PDEs. So in this case, G dagger is some operator that arises from some PDE. So you can think of, for example, as G dagger as being the solution map of the PDE. So for example, it might map the initial condition of some PDE to the solution at some fixed time in the future, some big capital T. But I'll be giving examples of G daggers that arise in the context of PDEs. And in this context, data-driven operator learning is effective for building Segre models. That is, models which are cheaper than traditional numerical solvers. Cheaper than traditional numerical solvers while retaining accuracy. And most of the past work, the work of the past few years, has focused on the use of operator neural networks. So operator neural networks, generalized neural networks, in a case where the input
Yeah, we lost you for the last few seconds there. I'm sorry. We can't hear you.
Sorry, for some reason my my Zoom just disconnected me. Okay. 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 Can you see this?
Yes.
Okay. So as I was saying, numerical solvers are in this sort of high complexity, but very, very low error domain. And the goal of operator learning broadly seen for these sort of problems is to be in this sort of much lower complexity area. So they're much faster than traditional numerical solvers, while maintaining a sort of low error. And in practice, they don't sort of achieve the errors that numerical solvers can, but they can be pretty close. In some cases, they can be sort of 1% error. And most of the past work has focused on the use of operator neural networks. So there are many operator neural networks. Some of the most notable are the Fourier neural operator, or FNO, and DeepONet, deep operator network. But there are many to choose from, and I'll be comparing our method against some of these methods. Okay, so in this talk, what I'll be discussing is a family of kernel-based methods, which are simple, fast, and competitive in accuracy. So if you can if you go back to my plot here, I'm going to present a family of methods which are in red here, so in the sort of same level of complexity, accuracy as operator neural networks. And in fact, I'm going to argue that often they are better than these operator neural networks. And they have the virtue of being very simple, fast to implement, and then there's therefore very natural benchmarks against, very natural benchmarks for more complex methods. So before trying an operator neural network, I'm going to argue that our method should be the sort of first thing you should try because it's very easy to implement and it'll give you your results very quickly. I'm also going to be talking about a sort of broad other methodology, which is in this sort of very low complexity domain, and that is linear regression. It can be seen as a particular case of our method. But in this case, it sort of has either higher error, it depends on the problem, but it sits in this sort of very low complexity area, and therefore it can be very attractive if you're trying to get a very low complexity method, and this can be interesting for certain applications. Okay, so one of the things that's important to understand about data-driven operator learning is how do we measure the performance of different methods? And there's been this very nice paper called the cost accuracy trade-off in operator learning with neural networks, published in 2022. And what they argue is that the correct way to evaluate different methodologies is through the cost accuracy trade-off. Because if we're trying to build effective surrogate models, what we need to measure is not simply the accuracy of these methods, but also how costly they are to, when at evaluation, when we want our answer. And therefore, you have to balance out these two needs: how costly it is versus how accurate it is. Because if the only thing you measure is accuracy, then the best method is actually traditional numerical solvers. They give you the best, at least currently, the best accuracy, but at a high cost. And so sometimes it's advantageous to look at lower accuracy models if they have much lower cost. So to measure this performance, so in terms of the accuracy, for the remainder of this talk, the accuracy will be in terms of the relative risk. So what this means is that in order to measure the accuracy of a specific learned operator, we're simply going to look at a test set, and we're going to measure the relative error in some norm, typically the L2 norm, against the true G dagger. And we're going to just average this over a test set. In terms of cost, there are sort of two costs that come into play for these methods. The first is the training cost. It is, since these are data-driven methods, is how much cost you incur at training. So for example, for neural networks, it comes in the form of having to run gradient descent, but also in terms of how much data do you need to achieve a certain level of accuracy. And for this, there aren't exact ways to measure the cost of different methods, at least not right now. But there are general qualitative metrics, and I'll be arguing that our method sort of ranks very favorably in terms of training cost. The second one is what actually this paper here, this 2022 paper, was concerned with, is the inference cost. Once you've trained your model, how costly is it to evaluate it on a new test point? And for this, there are actually rigorous ways of measuring the costs, and this is typically in floating point operations. And I'll be comparing our method against other methods also in terms of this metric. Okay, so now that you have a sort of general picture of what operator learning is and the challenges that come with it, I'm going to propose a general framework for operator learning with kernel methods. And this is going to be sort of an alternative to the neural network-based approach that have existed or have been researched previously. So like I said, typically the operator learning problem is trying to solve this sort of interpolation or regression problem, but where UI and VI are infinite dimensional objects. They live in function space. And so, of course, you can't give these to a computer. You have to discretize. So a more specific, precise way of describing the operator problem is as follows. We're going to assume that we have measurements of UI and VI. And these measurements, UI and VI, are going to be represented by bounded linear operators, so phi and var phi, that map these function spaces to a finite dimensional space Rm and Rn. And so the more precise version of operator learning is given these finite dimensional measurements, phi and var phi, of these functions of n samples, we wish to approximate G-dagger. So a prototypical example of measurements that you can have is pointwise measurements on a grid. So you can imagine that U and V are functions and that you measure these functions on a sort of grid of your domain. And that given these grid values, you wish to approximate this true G-dagger. But in general, our methodology can handle any pointwise any measurements beyond pointwise measurements, as long as they are bounded linear operators. Another thing to keep in mind as well is that in operator learning, typically people assume that the data that you get, the training data that you get, is sampled IID from some underlying measure mu. And then therefore the UI and VI induce some measure which is given by the this measure mu and the push forward by this operator, this true operator G-dagger, supported on this space. And one thing to keep in mind is that the operator learning problem generally depends both on the operator you're trying to learn, so the true underlying operator, but also on the underlying measure mu from which you're sampling your data. And I'll be giving an example to show that changing the measure mu can actually change the difficulty of your learning problem dramatically. Okay. So our method can be summarized by the following diagram. So we have U and V, which are function spaces. You have this unknown G-dagger that maps U to V. And our approach is going to first to define reconstruction operators. So you have these measurements phi and var phi that project the functions to finite dimensional spaces. We are going to define reconstruction operators sin chi, which are going to go from these finite dimensional measurement spaces back up to the function spaces U and V. So these are unknown right now, but we're going to define them. And once we've defined these reconstruction operators sin chi, this induces a function f dagger, which is vector valued. So it maps Rn to Rn by the following procedures. It starts in Rm, so a finite dimensional space. It goes through the reconstruction operator psi to the function space U, through G-dagger to this function space V, and down to the measurement space through this measurement operator var phi. And once we define the reconstruction operators sin chi, we can then learn the finite the map f dagger, which is a vector valued map. And in both cases, what we're going to do is we're going to define these reconstruction operators and this recovery f dagger using what's called optimal recovery maps and the optimal recovery method, and through operator valued kernels. And I'll be going into greater detail as to what this means. Okay, so the first step is to define these reconstruction operators sin chi, which goes from the finite dimensional space to back up to the infinite dimensional function spaces. So we're going to assume that U and V are reproducing kernel Hilbert spaces arising from two kernels Q and K respectively. And then once we've done this, we can define our reconstruction operators as optimal recovery maps. So what does this mean? So optimal recovery maps are defined in the following way. So it takes in this vector phi of U, which belongs to Rn. And what it looks like, it looks at all functions in the space U that agree with the data, meaning that if you pass W through this measurement operator phi, it agrees with the data you've been given. And among all these possible candidates for the reconstruction of U, we're going to select the one with minimal norm. And likewise, we do exactly the same operation with var phi. We look at all functions in the vector space in the RKHSV that agrees with the data, and we select the one with minimal norm. And the reason why we do this is because these are min-max optimal recoveries of U and V respectively. And one of the nice thing as well is that they have closed form solutions. And these are given by the representer theorem for kernel interpolation. So if you're familiar with kernel methods in general, you might have seen this formula before. So suppose that we're in the particular case when phi and var phi are pointwise values of these functions, meaning that phi takes in a function u, and it gives you its function values at a specific set of points, not necessarily on a grid, but it could be any points in your domain. And likewise, that var phi takes a function v, and it gives you pointwise values in the domain that you're considering. Then you have a closed form solution, and it's this simple standard kernel regression solution, which is given by these formulae here. And so what this amounts to is simply solving a linear system to get these closed form solutions. Okay, so once we've done this operation here, we've defined our reconstructions psi and chi. And our goal here is to learn this function f dagger, which is vector valued, right? And so as a reminder, what it does is it goes from Rm, this measurement space, it goes through the reconstruction operator psi, which we've defined, through this unknown operator g dagger, and back down through the measurements var phi. And once we've recovered this f dagger, we can define a recovery of g dagger by doing the inverse operation, meaning we start in U, we go down through the measurements phi to this measurement space Rm, we go through f that we've now learned, and back up through the reconstruction operator chi, which we've defined previously. And this gives us a recovery of the true operator g dagger. So the way we're going to do this is essentially in exactly the same way, using the same principles. So if you're familiar with kernel methods, you know that to do what I've done previously, which is define the optimal recovery maps, you have to define a scalar valued kernel. That is a kernel that takes in two inputs and outputs a scalar. Now here, the big difference is that f dagger is now a vector valued function, meaning it maps Rm to Rn, where n is greater than 1. And so for this, there's a simple generalization, which are called vector valued reproducing kernel Hilbert spaces, which are induced by matrix valued kernels. So in this case, gamma is a function that takes in two inputs, Rm and Rm. And instead of outputting a scalar, what it does is it outputs a matrix, so a linear map on Rn. And once you've chosen a gamma, a matrix valued kernel, this induces some reproducing kernel Hilbert space H gamma equipped with some norm induced by gamma. And so our technique to approximate f dagger is exactly the same as before. We simply look at all functions within this RKHS that agree with the data. So here these are the data here are vectors, and we're going to select the one with minimal norm. And again, similarly to the previous case, this map can be expressed in closed form in a way that's similar to what I've shown you previously. And again, it amounts to a linear solve. And again, for pointwise measurements, so this is the most common case in operator learning for PDEs, then the final expression for recovery of G is given by this expression here. So I don't expect you to understand exactly what's going on here, but essentially, this first part here is our f. This is our learned f. And then this first part here, the second part here, is the reconstruction operator chi, which goes back up to the function space. So here, this is a map that maps Rm to Rn, and then this part here goes back up to the function space. Okay, so this is a very sort of general framework, and in practice, there are many operator value kernels to choose from. In fact, there's essentially a limitless possibility, and it's not clear which one one should choose. But there's a very simple choice of matrix value kernel, which is given by a diagonal kernel. So here, gamma takes in 2 inputs, and what it does is it takes a real value kernel, so this is a scalar, and it multiplies the identity matrix by this scalar here. So essentially, this produces a matrix which is diagonal and has identical diagonal entries given by this real valued kernel, this scalar valued kernel. And the reason why this is a very simple choice is because essentially what it amounts to is recovering the vector valued function, or this f dagger, which is a vector valued function, independently component wise. So what this means is essentially you fix every component of Rn here, and you think of this as being a scalar valued function, and you recover each one of these independently from all the others. So again, this is in the framework of like optimal recovery. It amounts at looking at the component for each component J, at the one that agrees with the data, and at all the candidate functions that agree with the data, and selecting the one with minimal norm. And you can do this independently for every component. And again, this has a closed form solution where component-wise is given by this kernel interpolation formula. So this is a very simple choice of kernel, and it doesn't it doesn't explore all the possibilities for matrix value kernels that you could choose to apply to this framework. But in fact, it's a very attractive choice for several reasons. The first is that in order to define this kernel, you have to simply specify only one thing, which is this scalar value kernel S here. And this can be any standard kernel that's used in the literature, such as the Matern class of kernels, the squared exponential, or even the linear kernel. And in this case, this is equivalent to doing linear regression. And this simple choice has several really nice advantages. The first is that it's very low cost in training at an inference, in part because it separates the problem, right? So if I think of recovering this function f dagger, since I'm recovering each component individually, it's simply equivalent to recovering n scalar valued functions independently from each other. And this is very efficient numerically, both at training and at inference. This simple choice of kernel, as I'll show you later, is already quite accurate in terms of accuracy. In fact, it's very competitive, and we've observed that it typically performs at least as well as neural network methods. It's also very simple to implement. There are several libraries that solve this problem out of the box. So for example, you could use the very popular scikit-learn library. And so in terms of programming overhead, it's very low, and it's a very good benchmark. You can get your answer very quickly and very easily. Finally, it also comes with convergence guarantees, which are quite new in this area of data-driven operator learning. And one thing I won't be talking about today is it also has an interpretation as a Gaussian process, and therefore it comes with uncertainty quantification. Okay, so now that I've presented the sort of general framework in our specific simple kernel method for operator learning, I'm going to move on to the numerics and the theoretical guarantees. But before I move on to these, I want to make sure that there aren't any questions from the audience. Okay, if everything is clear, I'm not going to move on to
Can I maybe ask a question quickly?
Oh, yes, please, please.
So regarding the speed, the inference speed,
Yes.
you still need to invert the matrix, right? For the kernel.
So this, you have to do this at training, but you don't have to do this at inference.
Okay. Can you maybe show the formula again?
So yeah, if you look at this, right, you can, at training, once you've seen your data, you have to invert this matrix S. But you can sort of keep this factorization. And at inference, the only thing you need to do is evaluate this this kernel here.
Oh, because you stay on the same grid in some sense.
Yes. Actually, I don't think I have a slide on this, but there's also a way to adjust for a change in grid at inference. And in this case, yes, you will have to do a new inference, a new solve, but this is not in the S kernel. It's in actually the reconstruction operators. I don't have a slide on this, but you can also handle this point. But if you stay on the same grid, then yes, you don't have to invert anything at inference.
Makes sense. Thanks.
Thank you. Thank you. Very good question. Okay, so in terms of numerics, what we did is we looked at, so we tested our performance against examples taken from two comparison papers. So the two comparison papers, one of them I've already mentioned is this paper on the cost accuracy trade-off in operator learning with neural networks. And what this paper does is that it compares many different neural networks, including FNO, DeepNet, PCA-net, and others. And especially it looks at the cost accuracy trade-off. And the second paper we looked at is this paper on a comparison between FNO and DeepNet. And we've taken the data from, so both of the authors from both of these papers have put their data on open access, so you can get them on GitHub. And we simply use their data to make sure that we were trying to compare really apples to apples compared to what they were doing. And we compared the sort of the best results they reported in these two papers against our method. And for all of these examples, the way we look in terms of accuracy, we looked at the best reported tests relative L2 loss. So you can think of this as a percentage. What is the percentage loss do you get compared to the truth? So we're very grateful to these to these authors for putting their data online so we could compare against them. There's a small caveat which says that in general, it's not always possible to obtain the exact data they used in the original experiments. However, you can think of the data that we used as being resampled from the underlying measure from which they sampled their data. But apart from this, we used the same exact data and we compared exactly against exactly the same models. So for example, so this is an example of a problem, which is the Burger's equation. So this is a time-dependent PDE. If you're not familiar with it, it doesn't really matter. The point is that here, the operator that you're trying to learn maps the initial condition of this PDE to the solution at time 1. And in this case, the initial conditions are sampled from some Gaussian random field with given covariance. And so for this example, what we found is that we're not quite as good as the best versions of FNO and DeepNet, but we're in the same ballpark and we're as good as DeepNet. So this is an example where our method isn't quite, at the level of neural networks, but it's very close using the Mattern kernel, for example. So we're very close in terms of accuracy. Another example is the two-dimensional Darcy flow. And so here, this is a very classical inverse problem. So here, what we're trying to map is the field U, so the permeability field mu, to the solution V for a fixed F. So here, this is what the G diagram you're trying to learn. So here, U is sampled from some distribution, which is not Gaussian. So in the previous case, the initial condition was sampled from a Gaussian distribution. Here instead, it's sampled from a Gaussian distribution given by this operator here that is then mapped through some binary function. So to give you an idea of what it looks like, this is an input. So here it's like a piecewise constant function, but it has discontinuities here. So here in red, you're at one value, I think it's 0.5. And in blue, you're at some, these are negative, but they shouldn't be negative. They're then passed through some exponential. But essentially, these are two values, and you have, sort of discontinuities here. And here, there's a sort of similar story. We're not quite as good as, as the best neural networks that are reported, but we're actually beating, we're actually beating, for example, DeepNet on this particular example, and we're sort of very close to the best neural networks that were reported in this paper. And this is with very little tuning, very little hyperparameter tuning. You can get these results very easily. Okay, so this is another example, which is the advection problem. So this is an example where, in fact, the two papers used the same problems, but they had one difference, which was the underlying measure from which you're sampling your data. So recall that at the sort of beginning of the talk, I had mentioned that the operator learning problem in general depends both on the operator you're trying to learn and the underlying measures from which you're sampling your data. And this is a good example of it. So here, again, this is not quite so important whether if you know this PDE or not, but the underlying problem is to learn from the initial condition the solution at some time 0.5. And so here, the two papers, they differ in terms of the measure from which they sample. So they're given by these formula here, but I'll just show you what they look like. So this is the first. This is the first paper. So here you can see that it's a wave. It's a square wave, but the only thing that's random here is the height of the wave and the center of the wave. So here, the only thing that can happen is that the wave can sort of go up and down, or it might go from left to right. And that's the only thing that's random. Points only differ, like sample points only differ in this sense. The second problem here, what's going on is it's taking a GP and passing it through some nonlinearity. And so what can happen is you can have multiple sort of waves. And you can have three, in this case, there are three, but you could have one, you could have two, you could have more. And also here, in this case, they're negative, but you can also have positive, whereas in this case, you could only have, I think it could be flipped. It could be positive or negative. But here, the big thing that changes is the number of waves that you have. And what's interesting is that depending on which data set you get, even though you're trying to learn the same operator, the accuracy you get is very different. So I should mention that the operator you're trying to learn is a linear operator. So in fact, if you use a linear regression in this case, you can think of this as using our kernel method with a linear kernel. Then you get excellent accuracy. You get something to 10 to the minus 13 accuracy, which is essentially as good as you can get. What's interesting is our method, our GP with a maternal kernel, in this case, beats all other methods. It gets 10 to the minus 3 accuracy. The best thing that was reported in the previous paper was 0.04%. So in this case, we're actually beating all the neural network approaches that were examined for this particular problem. But what's really interesting is once you change to the other measure, so once you look at waves which can have multiple multiple waves and the number of waves is random, what's interesting to note is that you get much worse accuracy across the board. So all methods do a lot worse. So here, the best accuracy you can sort of hope for is something like 10%, even using the linear regression model, which in a sense should be optimal for this problem because the map you're trying to learn is linear. And so in this case, all methods are much closer in accuracy to each other, and they're all doing much worse than the previous example. But again, something to note is that our method with a maternal kernel, in this case, also beats all neural network approaches that were proposed in the paper. Okay, a final example is Navier-Stokes. So in this case, what you're trying to do is learn the map that maps the the forcing term f on the right-hand side to the solution at some fixed time t. Here again, here are the accuracies reported, and so this is an example from the other paper, the second paper. And in this case, again, our method with the maternal kernel actually does better than all the methods that were proposed, all the neural networks that were examined for this particular problem. Okay, so these are the results in terms of accuracy. But one thing I'd like to emphasize is it's not really just about accuracy. It's about accuracy and complexity. Because even if you're doing better in terms of accuracy, if your method is more complex than others, meaning it has higher cost at inference, then it's not really suitable for this surrogate modeling problem. Because in many cases, what you're trying to do is you're trying to reduce your cost. And here, so these plots compare the complexity accuracy trade-off of different methods, and they're taken from this cost accuracy paper of different methods. And this is the cost accuracy at inference only. So on here on the x-axis, you have the complexity is measured in terms of floating point operations, and the accuracy is measured in terms of the relative L2 loss, and you have different curves for different methods. So typically what was observed in this paper is that FNO, which is in red here, typically has the best cost accuracy trade-off of all the neural network methods that were examined. What's interesting is that our method here, which is a single dot in black, actually is in the fairly sort of high cost area. So it's more costly than neural networks, but it seems to beat FNO for a given level of complexity. So here there's a gap in accuracy. So this is the Navier-Stokes example I've just showed you. And here we seem to be beating these other methods in terms of complexity accuracy. And one thing that's sort of difficult in terms of measuring complexity accuracy is that kernel methods sort of scale differently compared to neural networks in terms of cost, because they scale in terms of number of data points, not in terms of the number of parameters. But for a given level of cost, we seem to be beating the neural network methods. There's a similar story for the advection problem. So here, the best method you can do is a linear model, because the operator you're trying to learn is linear. So in this case, the linear model sort of has the best cost accuracy trade-off among, cost accuracy curve among all considered methods. And again, our method with a sort of maternal kernel is typically in a sort of high cost area, but it seems to beat a lot of the neural networks for a given level of cost. It has higher accuracy. There's one notable example I'd like to mention, where our method doesn't beat neural networks in terms of cost accuracy trade-off, is this example in structural mechanics. You can find it in the paper, in our paper, but also in this cost accuracy trade-off paper. And in this case, we are fairly accurate. So in terms of accuracy, we're comparable to all neural network methods. But in terms of cost, we're sort of in the higher cost domain. And so one of the sort of future goals, of these methods is to sort of try and push these methods in the lower complexity regime by looking at things like random Fourier features, which can lower the complexity of kernel methods. And a final example is the Helmholtz equation. And again, in this case, what we found is we're sort of beating neural networks in terms of the cost accuracy trade-off, even though we are sort of the higher cost area. So I mentioned that all of these cost accuracy plots are in terms of inference complexity, meaning once you've trained your model, how much cost you're incurring at inference for evaluation of a single data point. But there's also training complexity, and there aren't really quantitative metrics to measure this. But what we've seen qualitatively is that training for these of our method is quite fast. So if you have a workstation, it takes less than 10 seconds, even with something like 10,000 data points. And you get your answer really quickly. If you have sort of low data regime, maybe like a 1,000 data points, then you can do this on a laptop very quickly. You can do this in 5 seconds. One of the things that, if you're familiar with kernel methods, you'll know as well that typically you have to choose the parameters of your kernels pretty carefully. In some cases, the performance of your method is quite sensitive to the choice of hyperparameters. But for all of these problems, what we found is that hyperparameter tuning is very straightforward. And a simple grid search generally offers very good results, and you don't have to spend a lot of time doing some hyperparameter tuning, and sort of a large class of kernels perform very well and have very good performance in terms of accuracy. But like I said, future work could be pursued towards lowering the complexity of these methods, for example, via random Fourier features or inducing points, which would lower both the complexity in training and at inference. Okay. The final thing I want to talk about today is our theoretical guarantees, because these are pretty new in the operator learning sort of community. Neural networks don't really, at least currently, don't have many theoretical guarantees. But one of the nice things with working with kernel methods is that it's actually pretty straightforward to get these theoretical guarantees. So to do this, we have to make a bunch of assumptions. I will be going over them pretty quickly, but essentially they can be separated in like two parts. The first are the assumptions that you need for the reconstruction operators. So if you remember my diagram, there's sort of this going up and down part, and then there's this going left and right part. So the first set of assumptions are for the recovery maps, the reconstruction operators. These assumptions are very standard in the kernel literature. They essentially amount to some regularity on the domains of the functions you want to recover, some regularities on the functions you want to recover, so you typically need them to be embedded in some Sobolev space. And you also need that, for example, if you measure them pointwise in a grid or pointwise in your domain, that you need the collocation points at which you're measuring them to sort of fill out the entire domain. So these are for the reconstruction operators. There's a second set of assumptions, which are actually for the approximation of G dagger. So this is the sort of left to right part of the diagram. Again, the assumptions these are more specific to this problem, and they essentially amount to some regularity on the operator G dagger. So we need it to be Frechet differentiable, and we need its Frechet derivatives to be bounded. We need that the kernels that we're using to recover this function f dagger to be as well embedded in some Sobolev space of sufficient regularity, and you need your data to be sampled sufficiently well, essentially, to approximate G dagger. So these assumptions are more or less restrictive. Part of the work we're proceeding right now is trying to lift some of the more restrictive assumptions, especially when it comes to the data, how you sample your data or how you obtain your data. But given these assumptions, what you have is a sort of worst case convergence guarantees. So what this theorem says is that as you let your number of data points go to infinity, and as you let the resolution of your data go to infinity as well, then the worst case error that you get in some ball of the arcaceous that you're considering goes to zero. So this is a sort of worst case guarantees on the error that you can make within some ball. And in fact, you can obtain convergence rates that depend on the smoothness of the operator G dagger you're trying to recover, and on the smoothness of the functions that you're considering, so the functions U. And again, some of the future work that we're trying to pursue is to get stronger theoretical results by lifting some of the more restrictive assumptions that we currently have. Okay, so in conclusion, what we've proposed is a simple, low-cost and competitive kernel method for operator learning that is at least a good baseline for many tasks, and in many cases actually beats the state-of-the-art neural network methods for data-driven operator learning for PDEs. We also have theoretical guarantees for these methods using the kernel framework. The paper the paper is out on the archive and will be out very shortly in JCP. Thank you very much for your attention. I'll be taking questions if there are any.
Yeah, thank you very much. Thank you. Any questions?
Yeah.